Hi again. In this lecture we will take a look at how a battery electric powertrain is built and show in what way it is similar to a combustion engine powertrain. This is the principal layout of a combustion engine powertrain. To get a battery electric powertrain, we start by getting rid of the combustion engine and the fuel tank. Then we replace them with the battery, replacing the fuel tank, the power electronics, converting the battery's direct current into alternating currents for the electric machine, and the electric machine, converting electric power to mechanical power. The electric machine is capable of operating and producing torque at speeds all the way down to standstill. Therefore, there is no need for a clutch in a battery electric powertrain. Then we get this layout of a battery electric powertrain. To simplify the system, we can, from a system perspective, combine the electric machine and power electronics into one subsystem called electric drive system. Or sometimes we will simply call it electric machine and just assume that the power electronics is a part of it. It may seem strange to combine two such different systems into one subsystem, but it is a smart move since these two parts always require each other. In this way, we do not need to model the alternating currents feeding the electric machine, and we don't have to worry about oversimplifying our model, since the currents do not influence anything outside the electric drive. The only variables we need to model are the ones passing the borders of the subsystem, indicated by the red square, since only those influence other parts in our powertrain. We already do the same thing with combustion engines, but we have become so used to doing it that we often do not reflect over it. When we discuss the combustion engine, we always assume the fuel injection system and ignition system to be a part of the engine. So now we have a driveline which in one end has the electric machine's torque and shaft speed, and in the other end the traction force and vehicle speed. Just like for the combustion engine powertrain, we can describe how the torque and the speed of the electric machine relate to the traction force and vehicle speed with the transmission model. The equations are exactly the same as for a combustion engine powertrain. Since an electric machine can operate efficiently in a wider operating range than the combustion engine, there is less reason for having several gears to select from. Many electric powertrains therefore only have a single gear, while some may have 2 gears or maybe even more to improve efficiency or to extend the vehicle operating range without needing an unnecessarily expensive electric machine. This is another way of drawing the same powertrain for an electric vehicle. Here we can see that the electric machine is often placed directly at the driving wheel axle. Then there is no need for a drive shaft between the electric motor and the differential. Instead, the motor is often mounted in parallel with the driving wheel axle. The gear and the differential can then be integrated into the same housing. This is a photo of an electric machine, its gear and its differential with the final gear. All the main parts are integrated in one unit connected to the driven axle. Often this unit is called an electric axle. In this lecture, we have described the electric powertrain of a battery electric vehicle. It can be analyzed with the same transmission model as a combustion engine powertrain, with the main difference that it typically only has a single gear or 2 gears. Before we go on and analyze the electric powertrain's operating region in force and speed, first practice what you've just learned by doing the following exercises.